Let's take a look at blackbody radiation and its influence on the global energy balance. Some questions we ask include, what are the basic characteristics of electromagnetic radiation? What is blackbody radiation and how does it make life on Earth possible? What causes the greenhouse effect and how is the magnitude of this effect determined? How do clouds affect the atmospheric radiation budget? What are the most fundamental feedbacks in the climate system? These are all things we need to consider when getting ready to discuss the global energy balance. Now here we have an image of three familiar planetary bodies, Earth in the center, Venus to your left, Mars to your right, and I organized them approximately to their actual size relationships. So what you'll notice is that Venus, Earth, and Mars are different in color. They're different in the gases that surround them. We know that Venus has a very thick CO2-rich atmosphere, lots of water as well. The Earth has a mostly nitrogen atmosphere with a little bit of water, and Mars has a very, very thin CO2 atmosphere with very little water. So given that these planets are all in a similar place in space, they're all vaguely the same distance from the sun, why do they differ so much in appearance? Why do they differ so much in temperature and their behavior and the possibility of life? The Earth has a mean surface temperature of about 15 degrees centigrade. That's about 60 degrees Fahrenheit. Venus has a temperature, on the other hand, of 460 degrees centigrade or 860 degrees Fahrenheit, while Mars, on the opposite extreme, has an average temperature of about minus 55 centigrade or about minus 67 Fahrenheit, like the wind chills you get in Saskatoon. Are we just lucky here on Earth? Well, we have to consider size. The size of the planets differ. And it's the size of the planet early on in the solar system history that determines how much stuff it's going to get, how much material it can accumulate. That includes water and the atmosphere. So the Earth and Venus are approximately the same size. They collected about the same amount of these volatile materials. Mars, being a little smaller, got the short end of the stick there, got less water and less atmosphere. What it did capture at the time has been largely lost to space, again because of size. It's too small to retain those volatiles to the degree that Venus and the Earth have. Time. We've had some time pass, and during this passage of time, Mars has lost its atmosphere. The Earth is losing atmosphere. Venus is also losing atmosphere. But because they started out with more and they lose it at a lower rate, they've retained more. And the position in space. The further you are from the sun, the more volatiles you're likely to accumulate. Because early in the solar system history, the sun forced those volatiles outward. And that's why we have the gas giants, Jupiter, Saturn, Uranus, and Neptune. They were the hungry hippos cruising through the outer solar system, scooping up all of the volatile material that got blasted out there by the sun. So we happen to sit very close to triple point on the Earth's surface, the triple point of water. In this phase diagram of the vapor phase, the liquid phase, and the solid phase. So being near this triple point at the Earth's surface, we can have the water exist in all three states. That's important for us to live on Earth. So it sounds like the Earth is not too cold, it's not too hot, it's just right, the way bears like it. Now this brings us to electromagnetic radiation. We all know that the Earth is heated by the sun, and now you know that the sun emits about 50% of its energy in the form of visible light, in that range of wavelengths that we call visible light. So here we have a diagram of electromagnetic waves being transported through space. Along with this wave, we're fluctuating those electric and magnetic fields. The magnetic field variation is perpendicular to the electric field. If we have a single frequency electromagnetic wave, it's going to exhibit sinusoidal variability of both the electric and magnetic fields in space as the wave is propagated. Electromagnetic radiation is defined as a self-propagating electric and magnetic wave. All such waves move at a constant speed, c, the speed of light, which is equal to very close to 300 million meters per second. So when we talk about waves, we need to define some characteristics of those waves. Wavelength is the first characteristic we'll tackle here. It's defined as the distance between two adjacent crests or two adjacent troughs, and it's denoted by the Greek letter lambda. So here we see the wavelength lambda from one crest to the next crest. The wavelength would be the same if you went from one trough to the next trough. The time it takes for a wave to pass is time t. The wave speed is going to be the speed of light. The frequency is the number of waves that pass a point in 1 second. This is denoted by the Greek letter nu, which looks like a little V. The speed of the wave must be equal to the product of the number of crests that pass a point each second. That's known as the frequency, and the distance between the crests, the wavelength. So here we have lambda nu equal to c, the speed of light. What this means, the importance of this, is that the longer the wavelength, the lower the frequency. And we can see that redefined here as nu is equal to the speed of light divided by the wavelength. Electromagnetic radiation can behave as a string of particles called photons or as waves. So these photons and photon energy are going to be related to the frequency. Photons are the smallest discrete unit of energy that can be transported by electromagnetic waves of a given frequency. The energy of a photon is proportional to its frequency, defined here, where h is equal to Planck's constant. And Planck's constant is 6.63 times 10 to the minus 34 joule seconds. This must be going somewhere, you're hoping. This means that high-frequency photons have a higher energy that can break molecules apart, whereas low-frequency photons cause molecules to vibrate or spin, and this increased vibration and spinning makes things hotter. We can see the absorption and emission of radiation illustrated here. Might be a little bit easier to think of it in this context. Think of a campfire. It's warm if you're near. Don't get too close, but it's not going to hurt you, again, unless you get too close. Or think of X-rays. X-rays will hurt you if you're exposed to enough of them, and your relative distance doesn't matter that much. So X-rays are high frequency, damaging to your genetic code. Campfires will warm you up or burn the bottom of your shoes. The electromagnetic spectrum is the full range of electromagnetic wavelengths. That's everything from very, very long wavelengths that are kilometers in length to wavelengths that are very, very, very short. Gamma rays, cosmic rays. So short wavelengths are troublemakers. Long wavelengths you generally don't even notice. What you do notice is this range of wavelengths here, between 400 and 700 nanometers, or 4 times 10 to the 14th hertz to 7 times 10 to the 14th hertz. This is visible light. Our eyes evolved the ability to see this range of wavelengths because 50% of the incoming radiation from the sun is in this narrow band. So we don't need to know what's going on in these wavelengths or these wavelengths as much as we do what's going on in these wavelengths. Visible radiation, therefore, consists of the range of wavelengths between 400 and 700 nanometers, or a billionth of a meter. And again, about 50% of incoming solar radiation is in this visible range. The visible spectrum is all visible wavelengths. We know it as the color of the rainbow, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. I had to think about that for a second. Infrared radiation, or IR radiation, has wavelengths that are measured in microns, or micrometers as they're known now. This is 1/1,000,000th of a meter. About 40% of the sun's energy is emitted at wavelengths longer than 700 nanometers, and about 10% is emitted at wavelengths shorter than 400 nanometers. Microwaves and radio waves are longer than infrared radiation, and radio waves can have wavelengths measured in meters. Ultraviolet radiation, or UV light, has wavelengths that range from 400 nanometers down to 10 nanometers. And as I mentioned a minute ago, the sun emits about 10% of its energy in this range of wavelengths. X-rays and gamma rays have shorter wavelengths that have limited effects at the Earth's surface, but they do interact with the upper atmosphere. And because they interact with the upper atmosphere, we don't have to deal with them in the lower atmosphere. So that's good for us. Flux is the amount of energy or material that passes through a given area perpendicular to that area per unit time. For our purposes, flux is equal to the number of photons that pass through a unit surface area per unit time. Now, just to humanize these wavelengths a bit more, we'll start out with the dangerous rays here. Dangerous, short, high-frequency wavelengths. These include gamma rays and X-rays, into the ultraviolet range, which damages your skin, the visible range, safe. We get into the communication wavelengths, microwave ovens, cell phones, radio broadcasting towers, remote control devices, transportation of electricity, etc. Now, it's the changes in the number of sunspots and faculae that affect the flux of solar radiation, the energy coming from the sun, and therefore affect climate. Here we have a couple images of the sun in various stages of activity, relatively quiet in 1997, becoming active in 1998, and the sun gone wild in 1999, just before the millennium. We can see that here in X-ray radiance variation within the solar cycle. So these would be very short wavelength images. You can see the sun was very active in September of 91, and by 1995, it calmed right down. So in these two different wavelengths, UV versus X-ray, we see that the sun was quiet from 95 to 97, then activated in 98, more active in 99. And here's a cool image of the sun in ultraviolet frequency, focusing on charged iron particles. So to take a look at solar flux, one of the best ways to do this is to observe a solar eclipse. You can't stare at the sun without special glasses. In this case, we got some really cheap glasses, but you do need some kind of protection for your eyes and for any instruments you're aiming at the sun. In this case, I just aimed a camera at the sun. So took this guy down to Smith's Ferry a couple years ago, thinking no one's going to be there. Turns out a lot of other people thought the same thing. So I drove up to the top of the mountain to get away from everybody. It was a real circus down low. And what we saw was this. The sun is being eaten by the wolf in Ragnarok. One of the neat things you can see during the eclipse is what's called Bailey's beads, or the Bailey's beads effect. In this case, this is the sun barely shining through the surface features of the moon. So where you see a dark spot, that's a mountain or a crater rim, another mountain or crater rim, another mountain or crater rim, so on. So we can actually see topographic features on the moon with the backlighting of the sun. And then once totality is reached, you can notice some activity here, some prominences, prominence, a flare, another one over here, and you can see, just taking a distant look, more activity here, here, and here. I have a friend that was in Kentucky at the very same time during the eclipse, and his photos look exactly the same as this, except he has a really, really nice, gigantic refrigerator-sized telescope. A couple more images from that eclipse. Again, totality here, and the diamond ring effect as the sun first emerges. This only lasts for a second or so. So it's really difficult to get some of these images. But now that I've been through an eclipse, I'm ready for the next one. Now let's take some of that solar flux and throw it at the Earth. The figure on the left here illustrates the concept of flux with a relatively flat surface, but at different angles. If we're at the equator during the summer solstice, the sun is going to be directly overhead at noon. So that sun is going to be concentrated on a relatively small area, but very concentrated. This is why you get fried like bacon when you go to the tropics after you've been up at the higher latitudes for a period of time. At the higher latitudes, where we are in Saskatoon, near the North Pole, radiation is going to be spread over a much larger area. Because it's spread out over a larger area, it's less intense. The flux is lower. Same thing goes with the southern hemisphere. This diagram zooms in on this particular portion of the Earth's surface. If the Earth behaved as a non-rotating disk with a surface area of pi r squared, it would have an average radiation flux at the surface of 1,368 watts per meter squared. That's a number worth knowing. 1,368 watts per meter squared if we're on a non-rotating disk perpendicular to the source of the energy. So maximum flux. But we're on a sphere. And to make things worse, to make things even more complicated than this diagram, the sphere is rotating. So it's turning about its axis here. It's exposing a bunch of different angles of surface here, and this results in a rotating sphere with a surface area of 4 pi r squared, a much larger surface area. The average radiation at the surface is going to be reduced to 342 watts per meter squared. This is also worth knowing. In particular, 342 watts per meter squared for a rotating sphere, as opposed to 1,368 watts per meter squared flux for a non-rotating disk, again perpendicular to the sun. Looking at it in a slightly different way, at the equator, using an incandescent light bulb with a tungsten filament, I'm guessing, to provide our insulation. This insulation is going to strike a flat surface with a unit area here, which we'll say is 10 square centimeters. With the paper perpendicular to the incoming light, we'll get a maximum flux through this 10 square centimeter area. At the high latitude simulation, we again have the same incandescent light bulb. The same insulation is being emitted from that light bulb and reaching this place in space. But now we're orienting our flat surface with this 10 centimeter square opening at an angle. The result is much less insulation will pass through this area, so much reduced flux. Looking at it a different way, in the real world, we tilt our solar panels relative to our latitude. So if you're at the North Pole and you want maximum insulation, you would angle your PV panel, photovoltaic panel, at 90 degrees relative to the Earth's surface, because the sun is going to be off on the horizon. At 53 degrees latitude, like we experience here in Saskatchewan, we're going to tilt our panel away from the vertical. It's not going to be anywhere near horizontal either, but this is to obtain the maximum insulation, the maximum flux during the wintertime when the days are shortest. Moving further to the south, Hawaii is around 18 degrees north latitude, so this would be the optimal panel angle for Hawaii, and a little further south than that, 14 degree angle here. This is for winter flux, the maximum flux in the winter. These people have everything covered, or at least covered in a bad way, in that they have lots of different angles available. Hopefully this is pointing south. There's no hope here. This is I think it's a tourist hotel in the Alps, and they just went with it, whatever they could nail their panels to. So very, very inefficient. Very dark in this place. This brings us to the concept of distance. The inverse square law states that the further you are from a source of energy, the lower the flux. In this case, S represents the solar flux at some distance from the source R, and S sub O represents the flux at some reference distance, R sub O. So we can use this as the position of the Earth relative to the Sun. So our Sun sitting here, Earth here. The distance from the Earth to the Sun would be S sub O. The distance from the Earth to the Sun would be R sub O, and the flux would be S sub O for the Earth. Moving further away to the orbit of Mars, this flux S relative to this distance R. Doing some simple math, if you double the distance, the intensity of the radiation decreases by a factor of 1/2 squared, which is a lot less. It's 0.25. So for every doubling of distance, we decrease by a factor of 0.25, which brings us to temperature. It's a measure of the internal heat energy of a substance. We commonly use 3 scales. Most people use 2, really. The Fahrenheit scale, the Celsius scale, and the Kelvin scale. The Fahrenheit scale might seem weird at first, because it is. It has a freezing point of water at 32, a boiling point of water at 212 at sea level. There is a reason for this. I didn't know until recently, but now I do. Celsius has a freezing point of 0 and a boiling point of 100. Now, ironically, this is exactly the opposite of what Anders Celsius proposed back in the 1740s. He proposed the freezing point of water to be 100 degrees and the boiling point to be 0. And Linnaeus may have gotten involved and changed that, and there are some other people. That's an interesting story, but we won't go into that now. Kelvin represents absolute temperature. So in the Kelvin scale, named after Lord Kelvin, the freezing point of water is 273.15 degrees. The boiling point at sea level is 373.15 degrees. The absolute temperature on the Kelvin scale represents the heat energy of a substance relative to its energy at absolute zero, the coldest possible temperature. And here we just have a comparison, a side-by-side comparison. In terms of absolute temperature, temperature on the Kelvin scale represents the heat energy of a substance relative to its energy at absolute zero. This is what physicists use. This is what goes into our energy calculations, the Kelvin scale. It's listed as degrees here. It's not really a degree. It's called a Kelvin. Using the sun's temperature as a comparator here. On the Fahrenheit scale, the sun's temperature is close to 10,000 degrees, whereas on the Kelvin scale, it's 5773 or 5778 or 5770, something like that. And the sun's surface temperature in Celsius is around 5500 degrees. If you want to know more about the Fahrenheit scale, this is about a 5-minute video. It's definitely worth watching. Really cool. It's going to give you more respect to Fahrenheit, maybe, and maybe less respect to the crazy things going on in the 1740s, scientifically. Just to summarize, Fahrenheit used 7.5 degrees as the freezing point of water, 22.5 degrees as the body temperature of a human, and 60 degrees as the boiling point of water. This is because he was buddies with a guy named Romer, who discovered the speed of light, who thought this was a good idea. Fahrenheit didn't like fractions, so he multiplied everything by 4, giving us the freezing point of water at 32 and the boiling point of water at 212 degrees Fahrenheit. It's kind of scientific and it's kind of crazy.